Today I'm going to finish discussing greatest common divisors that I started during the last lecture. And after that I'm going to move to discussing Gauss lemma, or at least begin the discussion. We showed that greatest common divisors exist in unique factorization domains. But for principal ideal domains, we can even give a finer result for greatest common divisors. So let this pink line be our standing assumption. And if we assume that our domain is a principal ideal domain, and for these two elements A and B, let D be a generator of the ideal A comma B, of the ideal generated by A and B. So A comma B is equal to D. Then D is a greatest common divisor for A and B. And let us prove it. We first check that D is a common divisor for A and B. A is contained in the ideal generated by A comma B, which is also generated by D, which means that A can be written as a product of D and some element R, where R is some element from the ring R. So it means that D divides A. And similarly, B is also inside this ideal, generated by D. So using the same logic, we get that D divides B. And let's prove the second property. Let's assume that some element E divides both A and B. It means that both A and B belong to the ideal generated by E. But this means that the ideal generated by D, being equal to A comma B, since the generators of this ideal belong to E, it means that this whole ideal is contained inside E. And this containment, similar to this first line, we have that D belongs to the ideal generated by E. It means that E divides D, because D can be written as a product of E times some element of R. And this concludes the proof. It is interesting to note that if D is a greatest common divisor for A and B, then since D is an element of this ideal, A comma B, then D can be written as a linear combination of A and B. X times A plus Y times B for some elements X and Y from R. And you can compare this picture to Z, and in particular, if A and B are relatively prime, then A comma B generate the unit ideal, so 1 can be written as a sum xa plus yb for some elements and x and y from R. And we get an even nicer picture in the Euclidean domains. For principal ideal domains, we can prove that D is satisfies this nice property of being a generator for the ideal generated by A and B. But for Euclidean domains, we can actually run an algorithm to find what a greatest common divisor is. So this situation is even better. So we can run Euclidean algorithm to get to greatest common divisor. Let me show how this works. We again have that A comma B are not both 0. So we want to find an element D of R which generates the ideal A comma B. If we have n from R minus 0 to non-negative integers, if this is the Euclidean function, we want to use this to divide A by B or B by A and replace one of these elements with the residue. So without loss of generality, let us assume that the norm of A is bigger than the norm of B, is bigger or equal than the norm of B. Then we do division with remainder and get that A is equal to B times Q plus R1, such that either R1 is 0 or the norm of R1 is strictly smaller than the value of the Euclidean function n at B. If R1 is equal to 0, it means that B divides A, and in this case we get that D is equal to B. We get that A is equal to BQ. So A comma B is equal to BQ comma B is equal to the ideal generated by B. And so we can take B as the greatest common divisor. And in the second case, we get that a comma b is equal to the ideal generated by b comma b cubed plus r. I replaced a by this expression, r1. And by subtracting b from this expression q times, or by subtracting bq from this expression, we get that this ideal is generated by b comma r1. And now the value of the Euclidean function of b is greater than the value of the Euclidean function at r1. And so we again divide b by r1 with remainder, and we get that b is equal to r1 times q2 plus r2. And so b comma r1 is equal to r1 comma r1 q2 plus r2. So this is equal to the ideal generated by r1 comma r2. And here we also have two cases. Either r2 is equal to 0, and then this ideal is just generated by r1, or r2 is not equal to 0, and we have that the norm of r1 is greater than the norm of r2, and we continue. And since at every step we get that the value of the Euclidean function decreases, and since it takes discrete values that are bounded below, so we are reducing, so we are running the descending induction. It means that the algorithm terminates at some step, so that ri comma r or I plus 1 stabilizes to be just ri by the virtue of ri plus 1 just vanishing. And we take this ri to be a candidate for our greatest common divisor, because it will generate the ideal that we started with. I will now start a big topic of factoring polynomials. Let us first consider an example where our ring is Z. So we have a polynomial a of x with integer coefficients. We can notice that if a of x decomposes into a product of two polynomials b of x and c of x, such that both b and c have a smaller degree than a, smaller than the degree of a. Then a of x, considered as a polynomial with rational coefficients, is also reducible. And in general, if we have a homomorphism of integral domains, And phi tilde is the unique extension that sends x to x and extends phi. Then we can conclude the same property that if A of x is equal to a product of B of x and C of x with both B and C having smaller degree than A, then the image of A can be also decomposed into a product of two polynomials, and if degrees of both the image of B and the image of C are greater than 0, then we again get a decomposition of p tilde of A. So we can study polynomials A of x by considering their coefficients as coefficients in some other ring. And I will start with formulating a first lemma or a particular case about this observation. I would like to fix my standing assumption that R is a unique factorization domain and F is its field of fractions. And I want the base ring to be a unique factorization domain because I will be talking about factoring of polynomials over R. And for that I want factoring to exist, and I would like to not distinguish between prime and irreducible elements, which I can do in unique factorization domains. So the first lemma, which is one of the ways to formalize the previous vague idea. The first lemma is, let's take a polynomial A of x with coefficients in R, an times xn plus a1x plus a0 let's say that P is a prime element of R and R is a unique factorization domain, then the following assertions are equivalent. First, for every index I, P divides AI, so P divides AI, so P divides every index of A. Second, P divides the whole polynomial A of x in R adjoint x. And third, the polynomial A of x lies in the kernel of the map of the quotient map phi, extends R of x to R of x modulo the ideal generated by P, which is the same as saying first quotient out R by P, and then I join x. For the proof, let us first prove that 1 is equivalent to 2. So if I can write every coefficient of A as P times some Bi, then denoting by B of x the polynomial with coefficients Bi, so we have Bn, Xn plus etc. B0. And so we have that A of x is equal to P times B of x, because we multiply every coefficient by P and get AI. And conversely, from 2 to 1, if we write AX as such a product, then every coefficient AI of A is written as a product of P by the corresponding coefficient of B. And now I observe that 2 is equivalent to 3 by the definition of the quotient ring, because again, if P divides A of x, it is the same as saying that A is equal to P times some polynomial B, and it is the same as saying that phi of A is equal to 0, because it is phi of P times phi of B. And this concludes the proof of this lemma. Based on this lemma, we know that it is only interesting to study these polynomials whose coefficients do not have common prime factors. And therefore, we formulate the following definition. We say that the polynomial A of x in R adjoint x is called primitive if first its degree is greater than 0, so it is not a scalar, and second the greatest common divisor of its coefficients. So with this notation, it will be the greatest common divisor of an minus 1 through a1 and a0. Its greatest common divisor is equal to 1. And it will be useful to notice that the second condition an through a0 are co-prime if and only if they generate the unit ideal. So an through a0 generate the unit ideal. That is the ideal that coincides with the whole R. Now I would like to formulate, you could call it the opposite of the previous lemma. So let's take a polynomial A of positive degree. Then the following are equivalent. first, A is primitive. Second, for any prime P in R, this prime does not divide A in R adjoint X. And finally, for any prime P in R and the corresponding quotient ring homomorphism from R adjoint X to R mod P adjoint X, for any such choice, phi of A is not equal to 0. So indeed, A is primitive in the assumption that its degree is positive, if and only if it is not divisible by any prime, if and only if the greatest common divisor of its coefficients is not divisible by any prime number, which is equivalent to saying that any prime number does not divide the whole of A. And this is the same as saying that A is not of the form P times B, so it does not lie in the kernel of phi. Let me now state the lemma about prime elements of R considered as elements of the ring of polynomials. Let's take an element P in a unique factorization domain R. Then it is prime in R if and only if it is prime as the constant polynomial R inside R adjoint X. So let me prove this. The backwards direction is easy because if P divides a product of elements A and B in R, then we can consider A and B as constant polynomials. And by primality of P in R adjoint X, we conclude that either P divides A or P divides B. So now the forward direction. So let us assume that P is prime in R and P divides a product of two polynomials, A and B, in R adjoint X. Let us consider the homomorphism phi from R adjoint X to R quotient P adjoint X. Then by the previous lemma, or rather by the very first lemma, which is the opposite of this one, we have that phi of A times B is equal to 0 because P divides A times B. But note that P is prime in R. So it generates the A prime ideal. P is prime in R, so it generates a prime ideal in R, and it means that R mod P is an integral domain. And I proved or reproved last lecture that when we consider the ring of polynomials over an integral domain, we get another domain. But in this domain, we have a product of two elements, phi of A times phi of B, and it is equal to 0. And therefore, one of them is equal to 0. But this is equivalent to saying that P divides A, or in this case, P divides B, which shows that P is a prime element in the ring of polynomials, because we started with P dividing a product and concluded that P divides one of the factors. And this concludes the proof. Now I will formulate a corollary of this observation, that the set of primitive polynomials in R adjoint X is closed under multiplication. Gauss lemma states that if A and B are primitive polynomials, then their product is also primitive. And I will prove Gauss lemma by taking a prime element of R, I call it P, and proving that P does not divide the product A times B. So, because A and B are primitive, we know that a prime element does not divide neither of them. So P does not divide A, and P does not divide B. Let us prove by contradiction and assume that P does divide the product A times B. But we have just proved that P is prime in R, implies that P is also prime as a polynomial. So by previous lemma, P is prime in the ring of polynomials. So P divides either A or B, which is a contradiction to the assumption that A and B were primitive. And so P does not divide the product of A and B, and we can prove it for any prime, and thus we conclude that AB is itself primitive. And here is a very useful corollary of Gauss' lemma, which is also sometimes called Gauss' lemma. And it is the following. So let's say that A R adjoint X of positive degree is irreducible if and only if A is irreducible as a polynomial with coefficients with the in the fraction field. So this is the first time when I use this notation of f, which is the fraction field of R. And A is primitive in R adjoint X. So these two conditions. And in other words, we can say that if A is a polynomial with coefficients in R, and A can be factored with the coefficients in the fraction field, then considered back as a polynomial with coefficients in R, also can be factored. So if we can factor polynomial over the fraction field, then we can clear the denominators in such a way that A is factored in the original domain. A model example to imagine is the one that I formulated before starting the topic of factoring polynomials. So when R is Z and F is Q, then we can characterize when A is an irreducible polynomial with coefficients in Z. And let me prove it. First, the forward direction. We can observe that A is primitive because otherwise it would not be irreducible. Because otherwise A is equal to some prime element of R times B, and it is a non-trivial factoring over R. To show that A is irreducible with over F, let us prove by contradiction. So assume that A is equal to P0 times Q0 in F adjoint X. Then, by clearing denominators and factoring out common divisors of the coefficients, we can assume without loss of generality that A is equal to B over C times P times Q, where P and Q are polynomials with coefficients in R and primitive, and B and C are elements of R. So we first clear denominators, which takes out C, which takes C out of P0 and Q0, and then we get a polynomial with coefficients in R, and then we factor out common divisors of elements in P and Q, of coefficients in P and Q, and this is how we get this B in the enumerator. Then we get an equality of polynomials in R, with coefficients in R, B times BQ, and this is an equality over R. And we know that A and P and Q are primitive. By Gauss' lemma, the product PQ is also primitive, and so the greatest common divisor of coefficients of CA is equal to C, because GCD of coefficients of A is 1. And similarly, the greatest common divisor of coefficients of B, PQ is equal to B. But note that these two polynomials are equal, so their greatest, the greatest common divisors of their coefficients must be can only be different by a unit. C is equal to some invertible element unit times B. But from this, we see that B over C is in fact equivalent to a unit element of R. So B over C is equivalent to unit over 1. And this means that we got a product in R over R of A as a product of unit times P times Q. So it means, so this contradicts our assumption that A is irreducible. And this is how we verify the forward direction. Let me now prove the opposite direction. And I assume that A is irreducible as a polynomial with coefficients in f, and primitive in R adjoint x. And let us assume that A is factored as a product of two polynomials in R adjoint x. So because A is irreducible with coefficients in f, it in particular means that we cannot factor it as a product of two polynomials of positive degrees in R adjoint x. So this means that either the degree of B is equal to 0 or the degree of C is equal to 0. But we also know that A is primitive in R adjoint x. And so this means that any constant that we factor out of A must be a unit. So this further implies that the degree 0 factor must be a unit in R. And it shows that if we have a factoring of A into a product of B times C, then either B or C is a unit in this ring. And this is exactly the definition of an irreducible element. So A is irreducible in R adjoint x.